Bismillahirrahmanirrahim. The Honorable Professor Dr. Abdellah Salhi, our keynote speaker from Department of Mathematical Sciences, University of Essex, United Kingdom. The Honorable Professor T.S. Dr. Ch. Muhammad Zaidi bin Ghazali, Dean of Faculty of Ocean Engineering Technology and Informatics, University Malaysia, Terengganu. The Honorable Professor Dr. Abdul Fattah Wahab, the Chairman of the 15th UMT Annual Symposium 2021, distinguished guests, invited speakers, and all participants. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and salam sejahtera. I would like to thank Almighty Allah Subhanahu wa Ta'ala in this blessed morning. Alhamdulillah, we are still given health to participate in our UMT Annual Symposium 2021. I would like to take this opportunity to thank all of the participants who are still enthusiastic until today, which is our third day. In this morning, it is a great honor to have keynote speaker Professor Dr. Abdellah Salhi from University of Essex, UK. He was actually my PhD supervisor back then in the UK. Professor Dr. Abdel Salhi will discuss data privacy and optimization approach and a case study in cluster analysis. Before that, let me just remind all participants to mute your microphone during this talk, and please unmute it in our Q&A sessions if you would like to ask questions. Thank you. Now please allow me to read the short biography of our speaker. Abdellah Salhi is a professor of operations research in the Department of Mathematical Sciences, University of Essex, UK. After his PhD from Eastern University, he worked as a research fellow at the Universities of Leeds, Edinburgh, and Southampton before settling in Essex. He works on topics in operations research and data science. He designed the plant propagation algorithm and applied it to the challenging problems in design and optimization. His most recent work includes the design of new approach to protect the security of data. He has led many research projects concerned with operation at container ports, green distribution in online shopping, smart town centers, optimum pollination with honeybees, and others. His work appears in prominent journals such as SEM, Annals of OR, GORS, COR, to name a few. He co-organizes the yearly EGL workshop at one of the University of Essex, Greenwich, and UCL. He was head of the department from 2010 to 2016. So without further ado, I would like to welcome Prof. Dr. Abdellah Salhi to deliver the presentations. Please, Prof.
Thank you. Thank you, Maharani, for the nice presentation. Good morning, everybody, and thank you for inviting me to give this talk. It's a little bit early here, but I'm sure it's all right for you over there. Bear with me. I may be a little bit sleepy, but I'll try to keep up, okay? So my talk, as Maharani just said, is on data privacy. And what I'm going to do really is suggest or give you an idea for a new approach to protect privacy of data. So the talk will basically cover these points. What are the issues of big data? What is privacy and confidentiality? What is this approach that we are suggesting? And then it relies obviously on the concept of complexity theory, which we'll give briefly. And then if we have got time, I will go through an example and basically illustrate and show how this approach that I'm suggesting works, okay? And then we conclude. Right. So what are the issues of big data? Well, it requires storage, requires maintenance, transmission, and analysis. You would say that this is the same with small data. True, true, true. However, when data is large, then it's costly to do all of these things. It takes more space to store it, it takes more effort to maintain it, it's certainly more costly to transmit it, and this analysis also, even though we could use standard techniques, but they would be very, very slow because of the sheer size of the data. And therefore, all of these things, although common to small data sets, are actually exacerbated and exaggerated and magnified when we deal with big data. These are the main issues. The other thing is that when you try to share data, big data, what happens is that you tend to replicate it. So, you know, if you have got an elephant and then suddenly if you want to replicate, you have two elephants. So it's, you know, storage is a big issue. So replication and copying also leads to compromising the privacy and the confidentiality of the data. So if you try to copy your data to others and give it to others to analyze it for you, then you compromise your privacy because they know your data and your data contains information, and that's what compromises your privacy and confidentiality. Now, you could say, well, instead of copying the data or replicating it, why wouldn't we just give access to people to the data? And that's it. In that way, we will not have double the storage. However, if you give access to people to the data, then not only you compromise the security of the data, you also compromise the security of the whole enterprise or the whole company or organization. So actually, giving access is very, very risky. And copying often is much, much better because at least when you replicate, you only give away the data. If you allow people to access your organization, often you may risk to give away a lot more. So these are the issues. So from my point of view, actually, I think that the loss of privacy or the potential loss of it is the biggest issue which is inherent to big data. This is my own opinion. You may disagree. Why is that? It's because the bigger the data, the more that can be given away if not protected. So if you have got small data, then often there is little information included. When you have got a lot of data, then a lot of information is given away. I'll give you an example. Suppose I spy on you and I observe you every day, okay, or for a few days. So if I gather data on you for over a week, so I watch you in the morning, you get out, you take some people with you, and you're in your car, then you come back at midday, then you leave again. Okay, I could, over a week, I could, maybe deduce that these people are their families, or they, maybe they will leave after a few days, maybe they are going to work, maybe they are going to do sports, whatever. If on the other hand I collect data over you on you for a whole year, I will be pretty certain whether those people live with you permanently, whether they are your kids, whether you are going to work, whether you are going to do sports, etc. So the larger the data set you gather on a phenomenon or on something, the more information it contains. And therefore, when you give away big data, you give away a lot more information to the third party. Now, what is privacy? It is the non-disclosure of valuable information to a third party. This is what we call privacy. You don't want people to have access to it apart from those you allow to. And we must remark or note that data and information overlap, but they're not the same. Sometimes you have a lot of data, but very little information. Sometimes you have got data with a lot of information in it. Okay, so data and information are not always exactly the same. Data privacy is compromised when a third party is involved. So when you deal, you and someone else have got access to the data, then this privacy is compromised. Now, why do we need to share data? You would say, okay? You would say, well, my data is sensitive. I just will not share it. I will keep it to myself. But you can't, because sometimes you cannot store it. It's too big for you to store. Sometimes you cannot analyze it in-house because you don't have the capacity or the capability to analyze it. For instance, if I'm in the business of providing health services, okay, then my core business is health, not data analytics. And therefore, if I have got a lot of data, I will not necessarily be able to analyze it. Therefore, I need to share it. So sharing data often is necessary. We don't choose to share it. We are obliged. It is unavoidable. Okay. In most situations, it is unavoidable to share data. Okay, and therefore you must share it, which means that it is likely to be compromised. And therefore we must find ways of protecting it, protecting its privacy and its confidentiality. That means this problem of confidentiality preservation and privacy protection is necessary. It's a problem that we have to face. There is no running away from it. Why? Because not every organization has got the capability to deal with the data on its own without asking other people, a third party, to come in to analyze it for them or to have access to it. So it is an important problem, and it is, if you like, exacerbated by big data. Because when it's small data, you could always deal with it. You could always, kind of find out, see through it because it's quite small. When it's very big, there's no way you can just do it with ordinary techniques or approaches. Now then, how do people preserve or protect privacy and confidentiality these days, or traditionally? Well, there is the administrative way. If you give data to people to analyze it, you get them to sign a contract in which they say that, well, they are not going to show it to anybody else. Okay, so this is the, if you like, the contract approach. The only snag with that, of course, is that people move. So for instance, if you give your data to an organization, the organization uses or asks one of their workers to look at the data. This person might have a copy, and then they may leave while they are staying with the company. Maybe they're not going to do anything, but once they leave the company, they don't work for that company anymore. They may then be free, or able to show the data or to exploit it themselves. And therefore, this approach is definitely not secure. The technical one is through encoding. This is what everyone knows. This is the way we do it. So you pick up the data and you encrypt it, okay? And there are ways which are known as homomorphic encryption and somewhat homomorphic encryption, okay? So it's not exactly homomorphic, it's less than that. So what happens there? You have got your data set D and you encode it into D dash. You analyze the encoded data D dash, and then you interpret the results for initial data set. And so the only problem with this is that some operations may not be carried out on the encrypted data. There'll be some functions which cannot be computed on D dash. And this is why we call it somewhat. If we had a fully homomorphic encryption system, then we would be okay. But because it's, on the encrypted data, we cannot do everything we could do on the original data, then it is known as SHE. Okay, so we call it an SHE encryption system. Now, people then looked at that and they said, okay, but this is somewhat homomorphic, is not exactly what we want. We want fully homomorphic. And so they went and they created that, okay? And so in this system that we call FHE, or fully homomorphic encryption, the encrypted data can be stored anywhere. This is the thing. So you can open it up to the whole world. Any third party, including hackers, cloud servers, can perform exploratory analytics operations, and they really cannot work out the original data. And any computing power available to the third party will not be enough to get usable information. So you cannot decode or you cannot break the code. So these are the three things that a fully homomorphic encryption has. It must encrypt data to be stored anywhere. Any third party can do anything they want, and they will not actually get to if you like get to break the secrets coding. And also computer power or brute force is not enough. You can do anything you want. It will take, if you like, hundreds of years to break it. And of course, the traditional crypto systems such as RSA, AES, the elliptic curve crypto systems, etc., they have properties A and C, they do not have B. That means third parties often can actually break the code somehow, okay? So that is the problem with the traditional systems. And this property B is the most challenging. Now then, the work that has been done on this encryption thing, or the homomorphic encryption, started in 1978. There are people like Rivest, Adelman, and Tusos who looked at how to secure banking data. And so they started already in 1978 to say, banking data or financial data is sensitive. Can we protect it? Can we make it, if you like, opaque to the third party? And then the system they suggest is not fully, if you like, homomorphic until 2009, when a guy called Craig Gentry, he was a PhD student, and he came up with a solution which is a true FHE scheme, a true fully homomorphic encryption system. Okay, so he developed that and he wrote his PhD thesis. It's all well known. Now, how does that work? Well, in this system, which is known as Gentry's system, the random noise is added to the cipher text. So they add noise to the data, the original data, so that then, if you like, in the encrypted form, you cannot read the original data. You cannot break through. The only problem with this system is that this noise grows quickly to prevent computing even simple functions. So when you have got big data, you add this noise, so the cipher, the resulting cipher text, if you like, becomes so cumbersome that you cannot do basic functions on that. For instance, you cannot do the product of two matrices, for instance, because the error is so big that the product is completely useless. And you need product of vectors, etc. If you wanted to do any data analytics, such as regression or clustering or whatever. Okay. So in fact, a practical FHE system must deal with three main problems. Now, what is the other thing that a proper or a practical FHE system must have? Okay, it must have these three things. The cipher expansion problem. So what you have actually developed, or the encryption of the problem. So the ratio of the encrypted data size to that of the original must be small. That means if, let's say, your data, you start with is an elephant. When you encrypt it, you don't want to end up with a herd of elephants, because then the data, the D dash, would be much, much bigger than the D that you start with. So which means it'll be much more difficult to analyze. So you don't want that. You want, if you have an elephant initially, when you convert it, you want to have an elephant, okay? Or you want to have maybe an elephant and a half, or a half an elephant. You don't want to have, if you like, 30 elephants, or because that just, if you like, if you inflate the data too much, then that's not good, because data, big data means computational work or expense. Computational efficiency. Now, the cost of homomorphic computing of an arbitrary function should be proportional in complexity to that of f itself. So if you have D on which you do some operations or some function, you can apply some functions f in D, then when you convert D, you make it into D dash, the function f must still be computable in similar proportion complexity. You don't want to have it then f becoming so difficult to compute, then if you like, then the conversion or the encryption is not good enough. So it must be, you must preserve, if you like, computational efficiency. And the third point, or the third condition, is security again. And the security of a scheme must be based on a hard maths problem. So it must be that whenever you create an FHE, it must be secure. That means if you want to break the code, then you need basically, as it says here, a security parameter S that you define, and then the amount of operations you will need to break would be of the order 2 to power S. Okay, that means the computations involved to break in the scheme are really too expensive, are too big for anyone to attempt them. Now then, the problem with this is that sadly no improved FHE scheme achieves the above so far. So far, Gentry's system, the RSA, all these systems are not really fully homomorphic and satisfy these three conditions. That's really the shortcomings, which means that the data really is not secure. Now then, what do we suggest? What do we suggest? Let's just recall or recap a little bit what we have said. So currently, you have D, you convert it into D dash, and then you analyze D dash, then you interpret the results for the initial data set D. That's what we do now using the the current encryption systems. So instead of that, what we are suggesting, we consider the initial problem, which we call P, and its solution X. Now we pick up the problem P, we convert it into P dash, and then obviously we transform it using some transformation T. Then we solve the problem P dash to obtain the solution X dash. And then from X dash, we deduce X using the inverse of this transformation. So this is the new approach. The old approach, or the current approach, concentrates on the data. We say we concentrate on the problem. So for instance, if you give me a data set and you tell me, go and do some clustering, the problem is clustering or regression. So our idea is that let's look at the problem, concentrate on the problem, forget about the data for a while, okay? We look at the problem first, and then we convert it, we transform it into another problem, P dash. So if it is clustering, what would be an equivalent problem that we can make it into? Then obviously we hope that the data, when we transform the problem, the data would be kind of implicitly be transformed and then basically hidden or protected. This is the idea. Now, this idea seems to be interesting. However, there are some questions. What is this P dash and what is T? How can you find P dash? And then how can you find this transformation T? This is what I'm going to explain to you. That is where the idea of complexity theory comes into play. Now, what is complexity theory? Well, it's really a discipline which characterizes the computational difficulty of problems. So you have a problem and another problem. Complexity theory tells you, this problem is more difficult than that one, or this problem and that problem are of similar complexity or similar difficulty, etc. Basically, it characterizes in a mathematical way the complexity to solve a given problem. And by the same token, it also characterizes algorithms. That's in fact, it's these two things, the problem and the algorithm, are kind of almost inseparable. Okay, so if you have got a difficult problem, that means the algorithms to solve it are not efficient. If you have got a nice problem, or you have a problem which you consider as it is easy to solve, that means that you have algorithms which run fast for it, which run, let's say, in polynomial time. Now, how do we do this characterization? Well, it is done by using what is known as worst case analysis, for instance, or probabilistic case analysis, etc. There are different ways of analyzing. The most common and perhaps the most well understood, perhaps the easiest to carry out, is the worst case analysis. That means you say, in the worst case, that means you know, given a problem P, you may find versions of it which are, you know, which are easy to solve because the data is small, or because the problem is special, or the, you know, there are some, or you understand it very well. There are a few things that you know to solve, but there are always cases where there is no way you are going to solve it easily. That means in the worst case. Okay, so this is a way to analyze data and to tell, and not to analyze data, to analyze problems and algorithms and say or characterize them. And the characterization of algorithms is in terms of the time they take to execute. So you have got, in the worst case analysis, you have got two types of algorithms. You have got polynomial time algorithms which solve easy problems, and exponential time algorithms which solve difficult problems. And therefore, with this, we have got then two classes, two clear classes. There's the P class, which is basically the class of problems that can be solved in polynomial time, and that means they are easy. You have got, for instance, linear programming is easy, systems of linear equations is easy, the minimum spanning tree problem is easy, etc. The NP class, it contains all the problems that can be solved non-deterministically in polynomial time. That means these problems, you can solve them, but only if you are lucky. That means non-deterministically. And so this class contains pretty much all the problems. Every problem can be put in that class, easy ones, difficult ones, except the very, very difficult ones, which are like the halting problem. If you know a little bit about computer science, you know the halting problem that what's his name that has been introduced by Alan Turing. Okay. Now, the NP complete class contains, now from this NP class, we extract, or we distill, if you like, another class, more defined, better defined, or special class, which is known as the NP complete class. And this concerns only decision versions. That means all the problems must be transformed first into a version which has got a yes or no answer. For instance, in the TSP, instead of trying to find the shortest tour, the decision version would just say, can I find a tour of length less than L, for instance? Okay, so it's yes or no. Does a tour like that, you don't say it is the shortest, you just say it is shorter than some value, so that the answer is yes or no. So this becomes a decision version. Of course, this is a simplification so that we can resolve these problems. However, this decision thing is not much easier really than the original problem, okay? But it just makes life a little bit easy for analysis. Anyway, the main thing here is that the NP complete class contains a lot of problems, okay? And these problems, they are actually, you know, when you try to solve these problems deterministically, any algorithm that you can find would run in exponential time, okay? In the worst case, of course. And so that's the characteristic of this class. Contains hard problems, okay, for which we do not know good algorithms. We do not know algorithms which run in polynomial time. We only know those that run in exponential time. And the other thing which is important in this class is that if you could solve one of them, any one of them, you could solve them all in polynomial time. That's really the great thing. So there are thousands of problems. Pick up any one of those. And if you can solve it in polynomial time, so could you all the others, which is great. And of course, there is the this is solving such problems is unlikely, because then you would prove for sure that P is different from NP, or P is equal to NP. Now then, what is good about this class, or why I'm concentrating on this NP class thing? Remember what we started? We started from data, the difficulty of data dealing with big data, and then the difficulty of dealing with or preserving privacy. I'm talking to you about about NP completeness. Now we say, what is he talking about? Well, here we go. I told you that I need, for my problem P, I want to find a problem P dash, which is equivalent. There we are. This NP complete class has got a lot of problems, okay? And as it happens, most statistics problems are in the NP complete class. Clustering is NP complete, data mining is NP complete, regression is generalized regression is NP complete, etc. And therefore, if they are NP complete, that means there are other problems, in fact, all the NP complete problems which are equivalent to them. Okay, so it's not difficult for me to find P dash. Okay, remember what I said before? Remember this question here, this one here, where I say what is P dash and what is T? There we go. So I have just answered it here. Our problem P dash is therefore in this NP complete class, which contains thousands. It's very rich. In fact, every day someone looks at a new problem that no one has looked at, and then they prove it that actually it is NP complete, and so it grows. So we have a lot of problems to choose from. Now then, it includes basic problems like the subset sum problem, the set covering, knapsack problem, the traveling salesman problem, of course, or TSP, the Chinese postman problem, and others, and clustering and data mining, etc., as I told you. Now, why I put the TSP and the clustering in red here is just because I will tell you in a moment that clustering can be converted into TSP. Now, this class, in fact, if we represent it, this is how it looks like. Not all of the problems, but some of them look like this. Why do we have a graph? Well, if you pick up one of these nodes here, this is a problem. Let's say number 2 here is a problem here, which is, I think it's click or whatever. I cannot read what's this number 2 here, but this is the name of the problem, okay? So 2 is a problem, and then it can be converted to any of one of these problems here. But it does not, for instance, go from here to there. Why is that? Because the link between 2 all the way down here, no one has bothered to find the transformation T. Every one of these links or these arrows or these edges is a transformation. So when you see here why people drew this graph in this way, is because someone has actually to prove that, let's say, problem number 110, what did they do? They picked up problem 2, and they transformed it into it to show that they are equivalent. And so every time you have one of these arrows there, that means the 2 problems which are linked, you can't convert one to the other. In fact, you can convert anyone to any other, but people did not bother to connect them all, because it suffices to find one transformation to show that a problem is NP complete. Once they have done that, they have published their papers, that's it, it's done. Okay, so people do not really convert everything else, except in some cases where the conversion itself is nice. It's a nice transformation. It's an easy one, etc. The good thing about these edges or these transformations, they are all done in polynomial time. They are all cheap to compute. So converting a problem to another in the NP complete class is cheap. Okay, that is the thing. Now then, let's look at the situation here. So we have got a hospital with a large medical data set that needs analysis. Obviously, the hospital cannot do it because their core business is health, not data analytics. And then grouping together patients, they want to group patients together according to some criteria. For instance, they want to have old people together, females together, children together, certain diseases which are contagious, for instance, together, etc. So it's a clustering problem, okay? So they cannot do it themselves, so they have to find a third party to do it for them, okay? But the data needs protection. Why? Because, for instance, insurers want to see the files. If, for instance, I have a life insurance and I want to renew the premium with my insurer, if they know that I am going to die very soon, I'm terminally ill, then suddenly my premium will go up very high, okay? So it's very important to preserve the medical data. You don't want the world to know what's wrong with you, okay? We don't want our medical data to be open to the world. So the hospital has got the duty of diligence to protect the data. So how can it be done? Well, it is a clustering problem because we want to break up these patients into groups, similar groups, let's say by age, the contagion of their disease or their illness, etc. So what do? We convert it into a TSP, okay? And then what we do, we show the third party, we show them the TSP problem, not the clustering problem. So the conversion, what does it do? It takes a problem which is a data analytics problem, which is clustering, and transforms it into another one, which is a logistics problem. It's a TSP, traveling salesman problem. Okay, so this is the idea. So problem P dash is the one that we show the world, not P. How this is done? Well, you pick up for clustering, you have objects to be clustered. These are cities. The dissimilarities between the objects are the distances between the cities. So what you have is, if you have got a group which is very different from another, then this is equivalent to having a big distance or long distance between two cities. Okay, so similarity, when groups are similar, then you represent them as cities which are near each other. When they are different, you represent them by cities which are far apart, you see? So the idea of TSP captures the clustering idea. And the objective here is to group similar objects in the same clusters and non-similar ones in different clusters. And in the TSP, you minimize the tour length, guaranteeing visiting the group of close cities consecutively. So when they are close, you want to visit them one after the other. And of course, if you want to find out who did this work first, well, actually, Lenstra did it in 1974, Clymer and Zhang in 2006, and Nazanin, I think, in 2007. I think Nazanin is, she's, I think, Malaysian, if I'm not wrong. Now, is data privacy protected? Now, so from this, the idea that we have suggested is actually privacy protected. Well, of course, we think it is. Look at these two factors. We change the context from a medical problem to a logistics one. So the outside world will think that we are actually trying to solve a logistics problem, not a context, not a clustering one. Therefore, they have no idea that our data is medical data, okay? Because the names will be just changed into numbers. Everything else, if you like, will be represented in terms of characteristics, in terms of numbers, and therefore they cannot tell. They are actually solving a TSP problem. The transformation of a database of names, personal data, etc., is very easy to do. Okay, it's cheap. So the answer is yes. Now, there are the three things that we said any FHE, any practical FHE must satisfy. Encrypted data can be stored anywhere. Yes, because if you give the TSP to the outside world, they will have no idea that it is, it's medical. We don't talk about patients, we talk about cities. We don't talk about diseases, we talk about other characteristics. Any third party can perform explore. Yes, they can take the TSP data, they can do whatever they like with it. There's no danger. Any computing power available will not be enough to get information, of course, because they have to guess, if you like. There are so many problems. They look at the NP complete the list, and there are thousands, and they would not really know which one comes from which. There's no way, because TSP can convert from any one of them, okay? And so they cannot really tell which one it comes from. And so now, the other things is it viable? Is this approach practical? Yes, because the data that the original data and the data for the TSP are of similar size. We are not going to inflate the problem in any way. Computational efficiency, we said that these two problems are similar in complexity, and the only addition is the computing of t, which is polynomial time. That's the only overhead. Okay, it's t, and t can be computed polynomially. This is all mathematical results which are known, which are established in computational complexity. What about the security? The security of the scheme was also quite solid. Why? Because, as I said, the guys, if the third party must guess the transformation, they must guess the problem, and even then they still cannot recover meaningful data because the data is completely transformed. Now then, let me just see if I can illustrate this. I don't have medical data to play with, so I use this problem here, which is that of clustering EU countries. This is actually a completely different problem in which we try to show that Turkey will fit in the EU. How do we do that? We try to use clustering. So if it clusters with different groups, which are of European countries, if it clusters nicely, that means it fits. If it doesn't cluster, that means it is always on its own, then it doesn't fit, okay? There are a lot of criteria which are known as the Copenhagen criteria to join the EU. Turkey tries to satisfy those criteria, but the EU says you have not, if you like, satisfy them. Anyway, that's a political problem, but we want to solve it mathematically. So what we did was to pick up the data, which is, by the way, open. You can find it in Eurostat and Turkstat repositories, and we normalize the scores using the normalization form here, and basically we just transform the data to calculate from the scores on the criteria of this Copenhagen conditions. We just use this mean score, if you like, approach, which is basic statistics. And so what happens is that we look at these different countries like Belgium, Bulgaria, the Czech Republic, etc., and the criteria, the population size, marriages, divorces per 100 or per 1,000, male life expectancy, etc. There are a lot of these criteria. There are many of them. There are something like 30 or 40 criteria. And then we do the transformation that I have just shown you, this one here, and that is why we end up with something like negative values, because we take the thing and we normalize it, and we take away the mean, if you like, and sometimes the mean is higher, and therefore we end up with negative things. So this table here of the scores, this is really the data of the clustering problem. Now we want to convert this data, if you like, to the data of a TSP, which is a distance matrix, and it is a symmetric problem. Okay, this symmetric TSP. What do we get? We get this. This is the data set. As you can see, this data here is symmetric. Everything is positive because there are no negative distances. The big numbers here, the 1,000 here, just says that in the TSP, you are not allowed to go from one city to itself. I cannot go from Belgium to Belgium or from Bulgaria to Bulgaria. So I put large distances so that I will never, because I'm trying to minimize the tour, I will never choose to take this edge, which is long by 1,000 or 1,000,000, because it just, I'm minimizing. I want to choose shorter distances. So this is just to say that do not go from one city to itself, okay? But the main thing is this data here and the one which I want to hide. This is the one I want to hide. This is the sensitive data. This is the one I want to show to the world. The world will never guess from this data the original one, okay? So basically what I have done by concentrating on problem P, and forgot about the data. The data, when I transform it, actually I hide it in an implicit way. Now the result here we go, so you can solve your clustering problem as a TSP. For instance, if I choose to do a 3 cluster, that means 3 clusters, and as you can see here, you see that Turkey goes nicely with Greece, Portugal, the UK, etc. And therefore Slovenia is the one which seems to be odd, even though it is a member, okay? So I could solve my problem in this way. And if I choose 7 clusters, again, I find that Turkey actually goes nicely with France, Spain, Italy, and the UK. Okay, while there are many countries, including Germany, which seem to be odd. Of course, Germany is easy to explain because it's such a big economy. It's much bigger than the rest, so it can form a cluster of its own. But the others, like Poland, Luxembourg, etc., that's quite odd, etc. Okay, so this is what we have done, and we could solve the clustering problem using TSP, and we get, if you like, viable results, and the data is preserved. Now, in conclusion, what can I say? We can say that loss of privacy is a big issue, and it is inherent to big data. Okay, it is inherent, as I said, because if you have big data, by definition, you have a lot of information in it, and therefore privacy is very, very sensitive, is weak. Current techniques for data privacy protection and confidentiality preservation are well below expectation. Why they are below expectation? As I said, Gentry's system, for instance, the FHE of Gentry, it's very difficult to compute. It's not applicable for big data. For tiny data sets, you could do a little bit, but not for practical data. Okay, so we don't know really any way that will preserve fully 100% the data. Our idea is safe and it relies on proven technology. So the idea that I'm suggesting is safe because all the maths exists and is very solid. For instance, converting a clustering problem into a TSP is very well done. It's done since the 70s. It's all done. Or the theory of computational complexity and NP completeness is well understood, and the maths is very, very solid. And so when you choose a problem, when you choose between these problems here, all this stuff is, if you like, these problems here, the transformations are all done, they're all known. If you want to cover your system even better, you could just invent another transformation, discover one. So you pick up a mathematician, you tell them, find a different transformation that has never been published, and that will save the day. Okay, and so it is safe because it relies on proven technology. It can be readily extended to other core problems. So now, what is the weakness of this method really is that for every problem, you need to do redo the problem, the solution. For instance, now I have shown you that for clustering, I can use TSP. I could use the maximum click. I could use the subset, some subset problem, anything, okay? But it works nicely with TSP. Now, if I wanted to do something like supervised learning, which is also NP complete, which is hard, I need to find a problem which converts to it. If I want to do classification, same thing. If I want to do regression, it's the same thing. If I want to do data mining, same thing. I need to find, so for instance, if you tell me, here is my data, can you please go and mine it, okay? But I can't do it, so I have to pass it to another person outside, but the data is sensitive. What will I do? I will find the data, I will find a problem which in the NP complete class, which goes with data mining, and then that is the problem. Then obviously I will generate, the data will convert the data to it, and then I will give that problem to the third party, and the third party will never know that I want to do data mining or what data I want to mine. They will solve the problem I will give them, and that problem could be anything. It could be again TSP, it could be, it could be maximum click, it could be a nonlinear programming problem, whatever it is. Okay. However, the data would be, if you like, converted as a byproduct of the problem transformation, and then by doing that, it will be protected and it will be hidden. Okay, and basically safe to give the problem to the outside world. Thank you for listening.
Okay, very nice talk from Professor Dr. Abdellah Salhi. And now we come to the Q&A session.
Yes,
Prof. So maybe there are some questions from the audience, Prof. Yeah. Okay.
Fire away.
All right, participants, now it's Q&A. Anyone ask to Professor Abdellah Salhi? We have
Assalamualaikum,
here.
Dr.
Okay.
Maharani.
Yes, please.
Can you hear me?
Yes, I can.
Yes, thank you. Professor Abdullah, my name is Tarmini. Regarding to the, we understand that complexity theory is the study of the limitations of algorithms. So about the P versus NP problems. So is there any recent study on this conjecture? I mean, P is equal to NP. And then if so, if there is a proving on this conjecture, so what is the implications of this problem to the data science or big data or computer science in general?
Well, we are not trying to to answer the question of P equals NP or not here. Well, that's not really the issue. I just mentioned it en passant because it is related. So it has really no bearing at all. Even if you prove that P equals NP or is different, it's really not a problem, because what we are saying in our case is just, if my problem P can be converted into a problem P dash, then I will, if you like, instead of solving P, I will solve P dash, and the data is converted, if you like, as a byproduct, and then it is hidden, if you like, because I changed my problem. Now, anything that happens with NP completeness, you know, whether P equals NP or is irrelevant. What we want to say is that the NP complete class is a store, is a reservoir of problems for us to choose from. That is all. Even if the issue is solved, it doesn't matter. Say, for instance, you could solve the NP-complete problems. You could all solve them efficiently. Who cares? That's good, because so that means if I can solve P complete P efficiently, I can also solve P dash efficiently. That's fine by me. What my problem is that the data of P is preserved, is protected, and the transformation will protect it. Okay?
Okay, thank you.
No worries.
Okay, thank you, Dr. Mimi. Is there other question from participants? We have here Dr. Sulaiman, Prof.
Yeah. You mean Sulaiman Muhammad?
Yes.
Oh, is he there?
Yes.
All right. Okay.
Dr. Sulaiman, you want to ask to our supervisor?
Fire away, Sulaiman. Fire away.
Thank you very much for this nice talk.
Thank you.
And the topic was interesting. And it's early here in Pakistan, by the way,
I see.
6:30. Yeah. And what I would like to ask that how we can analyze the complexity of the techniques we are applying to these data science problems in general.
Okay. They are already, well, of course. I mean, so if a problem is new, then it's, yeah, you have to analyze it. You've got to, if someone gives you a new problem in data analytics that is not known, then you will go and look at its complexity, and you apply the techniques of, like I mentioned, like the worst case analysis. And then you will decide whether the problem is easy or it is NP complete. Now, all the problems which are, if you like, commonly used or commonly tackled in data, they are already studied and they are already known to be NP complete. As I said, like clustering, generalized regression, data mining, classification, supervised or unsupervised, all these problems are known to be NP complete. There are papers which show that. So if someone tells you, I want to do some data analysis on the data, it has to be one of these problems. They want to cluster, they want to data mine, they want to, all of these problems are, if you like, are known to be NP complete. And therefore, it's just a matter of picking up one of them, picking it up, and then look into the set of NP complete problems. The graph I showed, the graph is only a small part. You look in there and you see which problem it converts to, and then you pick that problem as your P dash, and then you concentrate on that one. You change all the data accordingly, and then you concentrate on that one. Okay, so the analysis is done. If it's not done, as I said, if a problem is new and no one has analyzed it, you just have to analyze it. You will have to find, if you like, to show that it is NP complete. If it is not NP complete, it is easy for its P, well, it doesn't matter. Even if it's easy, you can still solve it. For instance, if someone gives you a set of linear inequalities, okay, which is easy to solve, you could change it into some graph theoretic problem, which is also easy to solve. The key thing is, if you have P, find P dash. Now I give you this list or this class of problems of NP complete problems because it does exist, and because most of the data analytics problems are NP complete. They fall in that class. However, if the problem you are dealing with is easy, even though the data is very big, then you could just find another problem which is easy that you call P dash, and then you transform the data to it. Okay. If the problem is not known to be easy or not easy, you have to analyze it. Okay. So you will prove that it is NP complete, for instance, that will give you a paper to publish. Every time you prove that problem is NP complete, or a problem can transform into another problem, that gives you a paper, and then that's it. So you have to do that, and then obviously you apply your results to the to the data you have got. Have I answered your question?
Yes, thank you very much.
No worries, you are welcome.
Thank you, Dr. Sulaiman. Maybe it's already Professor, Prof. Okay, we have here also Professor Dr. Norma Alias. Do you want to ask?
Yes. How are you, Prof? Abdellah,
Hey, hello
Salhi?
Norma. How are you, Prof.
All right.
Norma? How are you? All right?
Fine.
Very
Fine.
good.
Thank you.
Good,
All
good,
right.
good.
I love your presentation on big data and
Yeah.
then the data privacy. I learned a lot. Okay. I tried to study this new area for me. Actually, I'm
Thank you.
focused on the big data analytics and then the, supercomputer, high performance computing platform to solve a big data
Yeah.
simulation. So thank you very
Yeah.
much. I start a new journey.
Thank you. Thank you. Thank you very much.
Okay. For other participants, anyone will ask?
And I have another one question, Dr. Maharani.
Oh yes, yes, please,
Professor, I'm
Doctor.
sorry.
Please, it's
So,
okay.
Go on, Prof. Maybe.
is it possible to study the data analysis in terms of space complexity? I mean, the p-space problems, NP space problems, or NL?
Well, the space complexity is basically the analysis of how much space a problem requires to store it, to solve it. So the space complexity is not an issue. It's time complexity which is an issue. Space, basically memory. I don't know how. I don't know whether you are. I'm sure you are younger than me, but if you remember, at least my generation, in the olden days, in the 70s, memory was very expensive. Okay, we had very little memory. It was expensive. Then later on, it became very, very cheap. Now, for instance, you can store terabytes of data. You have got your computer has got maybe a gig of fast memory. In the past, it wasn't possible. It was very expensive. So space analysis, space complexity is no longer an issue. If you look in papers now, you go on Google and you type the space complexity, you will not find recent papers at all. In the 70s, yes, but not now. Now, time complexity is the issue. Why? Because even when we can produce very, very fast computers, problems like the TSP, like clustering, like, like maximum click, like all these problems in the NP complete class, they are all difficult to solve. So it's time complexity, which is an issue, not space complexity, if I understand your question.
Okay, yes, thank you.
Thank you.
Okay, thank you. So Dr. Mimi is our head of department, Prof.
Nice to meet you. Good to meet you, Prof. Mimi.
Yeah, nice to meet you, Prof. Thank you.
Okay, I just have one more question first.
Go on then.
I notice here when we transfer from the problem to the SP, right? And then you will get the symmetric matrix, right?
Yeah.
What if this matrix is not symmetric?
You can transform it into an asymmetric TSP. It's up to you. I mean, in this case, it's easier for us to transform it into a symmetric problem. If it's asymmetric, it is asymmetric. Now, the TSP, the symmetric TSP, just says that the distance between CT1 to CT2 is the same as the distance between CT2 to CT1. Obviously, sometimes when you go, for instance, if you measure the distance not as in meter, you measure it in time. So when you go, let's say one city is lower than the other, so one is high up in the mountain. So when you go up, it will take you 2 hours, but when you come down, it takes you 1 hour, and therefore the problem becomes asymmetric. Okay. That's all there is to it. There is nothing special about this idea of symmetry. And okay, so the matrix will still be, if you like, complex and very difficult for anyone to guess, because if you like, the numbers will be completely different from the, for instance, the example I gave you is a good one. I'm talking about medical data, where we are talking about patients, we are talking about this type of disease or disorders they have got, we are talking about their ages, we are talking about their gender, etc. We transform this data into distances. Okay, so we normalize it, and then so it doesn't matter whether the TSP is symmetric or asymmetric. The data, the matrix, if you like, the distance matrix, will not give away anything on the original data. You will never, for instance, look at the distance matrix and say, this number corresponds to the age of a person, or to their gender, whether they are male or female. You can't. You cannot guess anything at all, because this is a logistics problem, and this one is a medical problem. You know what I mean?
Yes. Okay. Um, I think it's already 10 o'clock, Prof, which
Okay.
is our end session.
Okay.
Okay.
Thank you.
So, all participants, finally we come to the end part of our presentation. We would like to say thanks again to Prof. Abdellah Salhi for your valuable
Thank you, everybody.
information and Tech. And hopefully the presentation will be beneficial to everybody. And before we end first, we're gonna have a photo session. Please, participants, can you open your camera? You stay on here first, Prof. You're waiting for participants to open the camera. Okay, I'm gonna count. 1, and then 2. Oh, count to 5. 3. Oh, start again. Okay, sorry. 1. Okay. Oh, I see. 1, 2, 3, 4, 5. Oh, freestyle, please, everyone. Prof, please. Okay, thank you very much. Thank you very much, Prof. Salhi. I hope we will see again here. Inshallah, next year maybe, Prof.
Yeah, I hope so. I hope next year, maybe it's a little bit optimistic, but possibly, yeah, why not?
Yes, inshallah.
Okay, thank you everybody, and
Thank you very much.
have a nice day. I'm going to bed now. I'm working tomorrow at 9, you know.
Allah, okay.
Okay, see you.
Have a good sleep, Prof. Okay, bye-bye. Assalamualaikum. Please, participants, after this we have invited speaker.